Hi guys, welcome back to my channel. It's your boy Method the Great. Today we have exact differential equation. It's actually the fourth method of solving first order differential equation. The general form of exact differential equation originates from an implicit differentiation which is expressed in the form of m dx plus n dy equal to 0. And this particular equation is said to be exact if and only if partial differentiation of m with respect to y is equal to partial differentiation of n with respect to x. Okay? The implicit function is actually a multivariable function, a function containing both x and y. It's function like this. Let's say given z of x comma y to be equal to some constant c. So this is representing an implicit function, and of course the method of differentiating an implicit function, we can let's differentiate both sides. We have z prime of x comma y. Or before then, it will interest me to let you know that the solution to this exact equation is actually that particular implicit function which the exact equation is formed. The particular implicit function from which the exact equation is what? Formed. So this equation actually is formed from an implicit function. You understand? So now, I am going to remind us how implicit function is being differentiated. You understand? So where I want to form an exact equation using an implicit function. Okay, so given this implicit function to be equal to some certain constant, the differentiation is we're going to be with respect to x and as well as with respect to y. So we're going to differentiate with respect to x first, which is partial differentiation of x, partial differentiation of z with respect to x, dx, plus partial differentiation of z with respect to y, dy equals to differentiating c is equal to 0 because it's a constant. You understand? So now, to differentiate this function, as you can see, we differentiate z with respect to x and as well as with respect to what? Y. Then differentiating c is equal to 0. So from here now, comparing this particular equation with this, you find out that m corresponds to that partial differentiation of z with respect to x corresponds to m, and partial differentiation of z with respect to y corresponds to what? N. So I was able to use this formula now as an equation formed from this implicit function. From an implicit function, you represent an implicit function to be in this form, and that particular form you transform it to is now called the exact differential equation, if and only if this condition hold. Alright? Okay, I'm going to give us an implicit function. I will use a live example of an implicit function, not just a formula relation, for you to understand it very well. Okay, given z of x comma y equal to x cubed plus y cubed plus 3x y squared equal to 5. Okay, so I want to form an exact equation from this implicit function. And then how do I go by that? How do I go about it? We have z prime of x comma y. From our formula here, we have partial differentiation of z with respect to x dx plus partial differentiation of z with respect to y dy equal to 0. That's the constant there. So the first thing we do now is equal to We're going to differentiate the whole of this function with respect to x, keeping y constant. So since y is constant, differentiation of any function that contains y alone will be equal to 0. So keeping y constant and differentiating with respect to x is differentiating x cubed will give us 3x squared. Then since y is constant, this is 0, then differentiating 3x squared with respect to x, differentiating x is 1, then 1 times 3y squared is 3y squared, so we have plus 3y squared, all dx. This part, we're going to differentiate the whole of this function with respect to y, keeping x constant. Since x is constant, this guy will be 0, then differentiating y cubed is 3y squared. Then differentiating this part with respect to y is 2y. That's differentiating y squared is 2y. 2y multiplied by 3x is 6xy. Equal to differentiating 5 is equal to 0. Then we'll add our differential value, the y, equal to 0. As you can see, this is now looking like the general form of exact differential equation. So we can equally still check to know whether the equation is exact using this particular condition. So we're going to differentiate this guy with respect to y. Remember, when you have the x here, definitely we're going to have m to be equal to this. That's comparing with this guy now. We want to check whether this particular equation I generated now, whether it is exact. So for partial differentiation of m with respect to y, we have the x here, we go with respect to y. When x is constant, differentiating 3x squared is 0. Then differentiating 3y squared will give us 6y. Coming to this side, n is equal to 3y squared plus 6xy. So differentiating this guy, partial with respect to x, because we have the y here, so we're going to go with respect to x here. Keeping y constant. Keeping y constant, 3y squared will give us 0. Then differentiating x here is 1, and 1 times 6y is 6y. From what we have here, it's evident that the equation is what? Exact. Because here the partial differentiation of m with respect to y is the same thing as the partial differentiation of m with respect to x is what? Is exact. Remember, what we are looking for now is we want to find this given equation using this exact equation we formed out of this equation. So just like for you to the solution to an exact equation is actually trying to ask you to find that particular implicit function from which the exact equation is formed. So I have formed this exact equation now. I am now solving the exact equation so as to get the original equation. You understand? Okay. So the next thing we're going to do now is we're going to compare. Remember, partial differentiation of z with respect to x is equal to what? This value here, which is m. Alright? So we can say now partial differentiation of, we can say there exists our function z, there exists z of x comma y, which is the main function, such that partial differentiation of z with respect to x is equal to m. So you can see partial differentiation of z with respect to x is m. That's the value here. And of course it is equal to 3x squared plus 3y squared. Okay? So what we're going to do now is we're going to use integration to find the value of that particular z, x of y. So integrating both sides, so what do I mean? We have Integrating both sides now, we have z of x comma y. I want you to understand that the integral of z, that's integral of the z, will give us the function z, implicit function zx comma y. Then integrating both sides, we have integral of 3x squared plus 3y squared with respect to x. So this is our m, so don't forget. So that we have z of x comma y is equal to, integrating this side is increasing the power to be 3 and bringing the 3 down to give us 3x cubed over 3 plus integrating this with respect to x. There is no x here because 3x squared, we're keeping y constant here. We are keeping y constant while we are integrating with respect to what, x. So this will give us 3. Since 3y squared is constant, integrating it, x will come in. We have 3xy squared plus some constant c, which is a function of y. The constant is a function of y because in this integration we are keeping y constant. Therefore, the constant of integration will be a function of what? Y. So when 3 cancels 3, we find out that we have z to be equal to s cubed plus 3x y squared plus some constant c of y. So since we are looking for the original, this is the function we are looking for. You understand? As you can see, we have our z function. As you can see, s cubed is here, s cubed is here, 3xy squared is here, 3xy squared. So what we don't have here is y cubed and the function y. So the only path we take now towards getting this function z is changing partial fraction of z with respect to x corresponds to this, and we integrate both sides. Then here is having the function attached to the y. So the next one now is partial differentiation of z with respect to y will be equal to the second one, which is equal to what? N. So this is the first instance. Then this is our function z. The only thing there is that we don't know what is c of y. You understand? Because the equation we use to generate this function now does not contain c of y. So we're going to find the value of c of y, which we'll substitute here to be able to give us the main implicit function. Alright? Okay, so we have the second instant. There exists also partial differentiation of z with respect to y, which is the second one now, that corresponds to what? N. Corresponds to n, and of course our n is 3y squared plus 6xy. That's the value of n. Meanwhile, we are now differentiating this function above because we want to find c of y. So this z is actually this function here. So I can have partial differentiation of z, which is s cubed plus 3xy squared plus c of y. We're differentiating it with respect to y, and everything is equal to n. 3y squared plus 6xy. Okay? So differentiating this guy with respect to y is going to give, of course, this is x, right? And then this is x, it doesn't contain y, of course. It will, okay? Where we are integrating z, which is this function here, will give us, with respect to y, this is off because it doesn't contain y. Differentiating here with respect to y will give us 6xy, okay? Then plus c prime of y, alright, equal to 3y squared plus 6xy, okay? Differentiating partial with respect to y, this does not contain y, is 0. Then differentiating this guy, y squared will give us 2y. 2y multiplied by 3x is 6xy plus. Differentiating this guy, since the function of y will give us c prime of y. Remember, our intention now is to find c of y, but what we have here is c prime of y. Definitely, we are going to make it the subject of the formula. Okay? So since we have 6xy on both sides, either we take 6xy to cross here, it will cancel out. We can just take out 6xy from both sides. Okay. We have to complete the solution. Let's still have our citation here. Z of x comma y. Okay. Okay. Let's still leave our original equation. So we have c prime of y is now equal to 3y squared. Okay. So since what we're looking for is c of y and not c prime of y, we're going to integrate both sides with respect to y. Integrating this guy with respect to y will give us c of y. Then integrating this guy with respect to y will give us 3y cubed over 3 plus k, says some constant k, and 3 cancels 3, so that c of y is equal to y cubed plus k. So since already we have known what c of y is now, remember, I told you guys that this is our function of z of y. This is our main function, this is our main function, but we don't know what c of y is, and then by differentiating this particular function with respect to y, we are able to get our c of y to be y cubed plus 3. Therefore, we can now substitute this c of y to this function. Therefore, our function z is equal to x cubed plus 3xy squared plus c of y. And of course, c of y now is equal to y cubed plus k. Okay? Then if you watch our main function now, which is this function, this is the given function from which we form the exact equation. So you can see x cubed here, you can see x cubed here, you can see 3xy squared, you can see 3xy squared, you can see y cubed, you can see y cubed. Then what you don't know here is what? Everything is equal to 5, which is some constant. But how do we make this some constants to appear now? Because if we have an initial condition, we can be able to substitute to know what the constant is. But then we can take this k to bring our constants together. K will cross to this side. We have z minus k is equal to x cubed plus 3xy squared plus y cubed. So that a, which is the constant a, is equal to x cubed plus 3xy squared plus y cubed, where z minus k is equal to what? A. So a is now representing what? The constant 5. So this is exactly this particular equation. So whenever you're given an exact equation, you are to manipulate, you are to solve the equation so as to get the implicit function from which that exact equation is formed. Thank you and God bless you.